What is your name? If you don't know your name, you have problems. Fortunately, you all remembered. Good job. My name will be Key. That's not what I meant to do. How do you highlight? Bing. There we go. Key. Okay. Note the Q update equation above. Duly noted. Consider a game in which an agent must choose between making a small immediate reward or seeking a large reward in the distant future. How would you adjust the parameters of the Q learning update equation above to cause the agent to seek a larger reward? They look fine to me. Use a value of alpha close to 0. That would cause it to give a lot to the existing value and not a lot to the new value. Use an alpha close to 1. Opposite. Gamma close to 0, that would cause it to not think about the future. It would only think about the immediate reward. You can see that, right? Lots of immediate reward, not a lot of future. Gamma close to 1, that is the answer because, oh hey, it doesn't highlight Greek letters. Because if gamma is close to 1, that means that it will have a lot of future value added into the current reward when considering what the Q value should be, which basically means the Q value depends on everything you're going to get all the way into the future. What if gamma is exactly 1? Yeah, then it stupidly thinks that a reward in the future is just as good as a reward right now. I wrote a chess playing agent, and I gave it a gamma value of 1. And it would get me in these corners where it could checkmate me in one move, and then it wouldn't. It would sit there moving around the board, wiping out my pawns and my everything else, and just smearing me like a cruel uncle or something like that. And it wouldn't kill my king, even when it could. And then at the very end, it had my king in a corner, and it could checkmate me in one move, and it just went back and forth, taunting me because it decided it could checkmate me in the future, and that was just as good as doing it right now. Humans tend to think that getting your rewards sooner rather than later is good, and usually it is, unless you have some really pathological case. So gamma should never be greater than or equal to 1. What happens if gamma were greater than 1? That'd be bad, because then it would put off getting rewards because it could get a lesser reward in the future, and that's obviously dumb. Just watch it be cruel to humans.
Yeah, so it just tortures human players.
That would be amusing. Hey, I guess there is a value for making gamma close to 1. It would be very amusing to just make humans suffer. Okay, so there's a place for it. Okay, how would you make a Q-learner robust to non-determinism? Basically, it's none of those, because those ones don't even make sense. It's going to be this one. Use an alpha value close to 0. Let's look at this equation. 1 minus alpha means 1 if alpha is close to 0, right? So a whole lot of what it already is, plus not very much of what you compute. What that does, if there's non-determinism, is it basically says every time something happens, we're only going to take a teeny baby step towards updating our Q value table. And that way, if it only happens 1 in 1,000 times, and you only take 1,000th of a step towards what it's supposed to be, then you've got it about right after one time. And do you see why that handles non-determinism well? Excellent. Okay. Draw a diagram of an actor-critic model suitable for you doing reinforcement learning with continuous actions. There are multiple correct ways to do this. Specifically, I know of 2. Let's do that one. I don't know how to paint inside a word processor, so I'll open my painting program. Most of you did it this way, and this is correct. So if you even had 2 boxes, I gave you some points for this one. So it wasn't too hard to get some partial credit. I tried to be lenient. But it's called an actor-critic model for a reason, because it has an actor, and it also has a critic. And just so you know, actor is another term for policy, and critic is another term for, could be a value function, or it could be a Q function, or a Q table, Q. If you even put the letter Q, I thought, yeah, you get it. So if you labeled them something like that, more points for you. And you didn't need both, one of them was sufficient. So the whole reason it's even called an actor-critic model is because before policy functions and Q functions and value functions were a thing, there was an observation that the brain seems to do actor-critic things. I think this emerged in philosophy or some region of that. And for whatever reason, someone developed an actor-critic model and somebody else came along and said, hey, that kind of fits what we're already doing with continuous learning and reinforcement learning, so they called their thing an actor-critic model. By the way, I don't know this happened. I didn't read about it. I just speculated based on hints I've picked up in the literature. So what I just said might be totally wrong, but I think it's right. The whole point of a policy is state goes in, and it computes actions. So an actor is called an actor because it decides what to do. It picks your actions. And so you should have had something looking kind of like that, indicating that the actor or the policy consumes state and produces actions. In other words, it says what to do in various circumstances. If you know your policy, you know what to do in all conditions, which would be great. Since that's really all we need, why do we even need a critic? If you had a perfect policy, what the heck good would a critic be? Yeah, it turns out if you had a perfect policy, you don't need a critic because, hey, stick the policy in, your robot does what it should. But how are you going to get a perfect policy? So it's not that we want a critic, it's that we need one in order to train the policy. So that's why it exists. Couple ways to do a critic. If you use a Q function, it needs two values fed into it. It needs to know the state as well as the action that you perform, and it computes something which you may have termed value or utility or goodness or awesomeness or cookie units, whatever. So, some indicator of how good the state action choice was. Okay, and if you drew this, so this problem was worth 15 points. I divided it up into 3 5-pointer portions, and so far we've done 10 of them according to the way I graded it. So 5 points were for just basically getting the idea of actor and critic, and I gave you 5 more for doing the inputs and outputs and arrows, basically showing how it all worked out. And then I gave the last 5 for how the thing was trained. This gave you guys lots of trouble. Apparently my wording is terrible. I apologize. Identify the inputs and outputs of each model. Got that. Also state how the target output values for each model in your diagram may be computed. Okay, what are target output values? Or target values? Yeah, this is saying, how do you know what you want these functions to compute? Those are target output values. Does that term make sense? If you gave me some way to determine what you wanted your value or goodness or utility to be, or if you indicated how to get an error signal that could be backpropagated into the critic, or if somehow you indicated how to train this thing, then you got it. So the answer for this critic is basically the Bellman equation. Or if you wrote out the Bellman equation, or if you gave me some equivalent of this function, because that's what this function is. This function tells you what the Q table is supposed to output. And because this is a Q function, it tells you what the target values should be. So it was right there on the page. You just had to kind of look up and think about it a little bit. But this is the target function. And this is derived from the Bellman equation. The Bellman equation doesn't specify to do this non-deterministic thing. So there's no step rate in the Bellman equation. But otherwise, it basically says that the value of your current state is step into the future and discount it and add rewards, and that's what you got. So this Q update function derives from the Bellman equation. Therefore, if you even had the word Bellman, I think you get the idea. The idea is take your future discounted reward, and that's what the value of this action in this state is. And how do we know how to train this one? Well, it turns out that backpropagation gives it to you. So if you take the value of this one and you backpropagate across here, then you now have an error signal that tells what the actor or policy is supposed to output. So if you put if I saw the word backprop or something like that on your diagram, then that kind of told me how to train the actor, and that's all great. So this is one way to have done it. Another correct answer would be to say the state feeds into both the actor and the critic, because this one is a policy or actor or policy, and it computes the actions. So far this one's the very same. And this one is a value function. It would not be correct to put a Q table here, because Q implies that it takes both state and action as inputs, and value implies that it only takes state as inputs and computes utility or something like that. By the way, I should also mention there are two types of Q tables. One takes state and actions as inputs and outputs a value or utility. Another takes only state as input and outputs the value or utility of all possible actions. Right? That's how we usually do it with discrete actions. But because we're doing continuous actions, and we assume you're doing continuous actions because that's what the actor-critic model was invented for, therefore we're probably using that form of a Q table. Okay, if you use this form of model, then once again, the utility is still computed by the Bellman equation, or something that suggests discounted future reward. So any way to estimate discounted future reward would be fine. How do you train the actor or the policy? According to the A3C algorithm, uses something called the advantage function. An advantage function is basically you take the difference between the value of the future reward and discount it, and the value of the current reward, and that difference is what should be the error signal to update your policy there. And if you did that, then you nailed it as well. And if you didn't do one of those steps, I took off some points because that's what you do on a test. So, but it displaced a bunch of white space. Okay. Which conditions are necessary for a Q-learner with epsilon greedy exploration strategy to be able to guarantee to find the optimal policy? Circle all that are necessary, don't circle any that are not necessary. Okay. This one, I've got to admit, was tricksy and wordy and all of that, but, well, we'll talk about why. Do you need to always exploit and never explore? No. Obviously not. That would kill you, or would kill your effectiveness. Does every state need to be reachable with some non-zero probability? Yeah. Absolutely. Technically, if it's not reachable, then you could say your policy's optimal if you didn't reach it.
What if you started there?
That's an interesting point. Although,
What if the unreachable state is the goal?
Yeah,
Well,
but it's still optimal for what can be done.
proving that's wrong does not prove that it's right.
Huh. That's an interesting point. Well, if you deliberately didn't put that one, you've got a good case against me, so when I return your test, please check that one. But here's why they usually say every state has to be reachable, because presumably there's other states reachable from that unreachable state, and it wouldn't be the optimal policy unless it was also optimal in those states. But of course, if it's unreachable, then you could say it doesn't matter how optimal it is in those states. So I guess it depends on practical versus theory. Okay, that one's slightly debatable, but the correct answer is yes, every state must be reachable with some non-zero probability so that you can go there and update your policy and value function in those states so that you can have an optimal policy. So you should have circled that one according to my key, unless you thought you shouldn't have, in which case, you're kind of right. Okay. Do actions need to be continuous? No, you can approximate optimality with discrete values just fine. Do actions have to be multidimensional? No. Does the Q table have to use sufficient granularity to capture the state space? I'm going to say a yes on that one because obviously you've got to represent the function. If you're looking at the whole problem with blurry glasses, how can you be optimal? I mean, it's just, well, the answer is yes. Okay. Does training have to continue until convergence? If it doesn't, you haven't trained your model sufficiently, so it won't be optimal. So yes. Okay. Then a lot of these were just absurd, and most of you saw through that and didn't circle them. So do you want me to read them all and talk about them? Okay. Let me just highlight the ones that I snuck in there and got you with. These ones I got quite a few people on. So the learning rate alpha must be sufficiently close to 0 if there's any non-determinism in the actions. I claim this is necessary. Yeah. Here's why. Remember this equation? Hey, where'd my equation go? Oh, yeah. No wonder it took a weird shape. It was fitting the same shape as that equation. That's messed up. Okay, well, there will now be no Q update version in this copy of the test. Alas. Remember that alpha thing? Okay. If you don't have a tiny little learning rate and there is non-determinism, then a single random chance will throw off your Q table, right? And basically that's not optimal. In order to get optimal, you have to absorb the non-determinism into your probabilities so that you actually have a probabilistically correct Q values. So this one should have been highlighted. The other one is this one. And let's talk about this one. The discount factor must be set to the same value used in the definition of optimal for the policy. Now, I got to admit that's wording, but here's what I'm talking about. What does optimal mean? Presumably, it means you maximize your total reward, right? But we talked about how are future rewards as good as present rewards? Usually people say no, but what if you think they're 90% as good as present rewards? And our Q learner is updating thinking only they're 80% good as present rewards. It's going to make different choices than the one that matches your definition of optimal. Does that make sense? In other words, you have to have gamma right. If the discount factor is not the same as the person who's defining what optimal means, then it's not technically optimal. Okay, well, don't worry too much about this one. It was worth 15 points. I took off 1 point for every mistake you made. I think there were like 15. I think there were 17 circles. Basically, most people got 14 out of 15 or thereabouts on this problem. So that style of grading ends up working very nicely. But I think you should have circled that one. So there. So you were right that in a lot of cases, optimal is not going to be well defined. And so I guess this question could have been worded, optimal has to be well defined, or you...
It must be set. So if this violated, I feel like this is also...
Okay. It is strong wording. I agree with that. I don't know. If we want to debate it, I'm not going to push back too hard because, you know, it's worth 1 point. I don't really care. But for right now, after I give your test back, get all picky and argue technicalities with me. But for right now, the correct answer, I claim this technically should be circled because if optimal is even a thing, the only way to hit it is if you're doing the same thing, right? Or if you're doing approximately the same thing. Because the decisions will differ. Easy case to argue that is this. Put a marshmallow of size 1 right here and a marshmallow of size 1.3 10 steps away and ask which marshmallow are you going to go for. Depending on your value of gamma, you'll go for this one instead of that one. And if the person defining optimal says you should have gone for that one and you go for this one, you have done something suboptimal. This is a case where there's no right answer. There is no true gamma in the world. Let's see. I did say exactly. Arbitrarily and exactly differ by infinitesimal amounts, right? So is arbitrarily close the same as exactly the same?
Arbitrarily close.
It's arbitrarily close. Okay.
Close enough to fit the same.
Your argument is arbitrarily close to being right, then. And therefore, technically you're right, but you differ by an arbitrarily small amount.
So can I have 0.999?
Sure. I'll give you 0.99999 of a point back on it. That works, yeah.
I think the argument that's strong.
Okay. Just in case I copy this test question and use it in a future test, I'm going to correct the question now to not say exactly, now it says about. Because if your gamma were not arbitrarily close to the true gamma, then it would be wrong. So there you go. I have formally admitted my question is flawed.